This is an illustration of the non-linear shooting method with secant method. So we start with the non-linear boundary value problem. Of course, it is of 2 points. So it is characterized by the two boundary conditions given for x equal to a and at x equal to b we have the values of dependent variable y as alpha and beta. The mathematical form is a generalized function of x, y, and y prime. We represent that with the with f as f of x, y, y prime. So how do we proceed? In this case, we solve several initial value problems of second order and see which of the initial value problem uh, that has a particular slope value, which of the initial value problems satisfy the second boundary condition. Of course, we start with the first boundary condition, and then we check which of the initial value problem of second order satisfies the second boundary condition. So how do we proceed? So we take a slope value from the first point and solve the problem, and if it does not match with the final boundary value, we repeat this process in order to facilitate the slope update process, because we do not want to apply random values for the slope. We define a non-linear function g of t equal to beta minus y of tb. So it is the final value of the function y with the slope t. So if we optimize the value of t in this equation, like the solution of a nonlinear equation, so that will facilitate our process of finding the optimum value of t, which satisfies the final boundary condition. So for example, this process can be done with the secant method. So we define the function, and in order to work with the secant method, we must have two values of t, for example, tk and tk minus 1. So with this equation, we can get a new value of tk plus of t, which is at tk plus 1. So by repeating this procedure several times, it is hoped and it has been found that we find the solution of boundary value problem. With the final value of t, we have to again solve the complete boundary value problem, and that completes the solution of boundary nonlinear boundary value problem. So we will illustrate this problem in this demonstration, like d2y dx squared equal to 1 over 8, 32 plus 2x cubed minus y prime. So this product of variable y and y prime, this makes this problem nonlinear. Boundary conditions are y1 of y of 1 equal to 17 and y of 3 equal to 43 by 3. We have from our reference book the exact solution for this problem that we will use in comparison. And here is an illustration that if we solve the problem with different values of slope, and slope is basically u of 1, which is also equivalent to y prime of 1 equal to y prime at 1 equal to tk. So several slope values will generate several solutions. So we have to find the best one which conforms to our exact value. So let's move on to see the demonstration in Microsoft Excel sheet. So here we are. The boundary value problem selected is here. And in order to solve this problem with the RK4 method, we have to first convert the second order differential equation to a, a system of two first order differential equations. For example, we define dy dx equal to u, and we define du dx equal to 1 over 8 32 1 over 8 times 32 plus 2x cubed plus yu, and u of 1 equal to pk. So we will make the we'll make a setup for our calculations. So the left column generates the values of x with a step size of 0.1. So we have values from 1 to 3, and then we define the the initial condition. Since we are not going to directly solve the boundary value problem, so we have y of 1 equal to 17, and our value of y prime is equal to u, and we perform the calculations for RK methods. So we have the corresponding k calculations. First k1y will be calculated, and you can, when you make a click on any column, so you will find how it has been calculated. So for example, you can see that the B13 value, it is in this column we have 0.1 times K12 value, which has been picked from here. It means that in the whole set of calculations, if you start making a change in any of the value of either y of 1 or u of 1, the whole set of calculations will be repeated. So you can check that for all calculation that C13 is equal to this particular expression. In Microsoft Excel, you have to perform these calculations very carefully. So I have written the boundary conditions also over here. Y of 1 equal to 17, y of 3 equal to 14.33. Here I have also an access to the exact solution, so that we will have for comparison. So for example, to this point, for example, I use a value of slope equal to 0. So I have some calculations for the solution y, predicted solution y, and a solution also in u. So let's see the picture. Over there we have the plot of column A, the x values, the y values, the computed value of y, and we have the exact solution value that has been generated from the solution given by our reference book by Professors Burden and Fields. So if we see the plot, so we have the exact solution plot. However, with the guess value of the slope, we have a computed solution much far away from the exact solution. In order to work with the secant method, we have to solve this problem again. So let's first record the values. For example, I have taken a value 0. I took the value 0, and the final value I got, I will choose the numerical value over here. This light pink, orange value. So I will pick it value to 21.0185. Okay. Now I will solve this problem again for a different slope values, tk value. In order to work with the secant method, we must have two initial approximations for t. So for example, I use a value over here -1. So the whole set of calculations will be repeated, and we can see in Microsoft Excel, that is the beauty, that we can see the set of calculations. So let me record the slope value. Over here, I use the slope value -1, and I got a final value. Let me pick it from here. This is the final value predicted by the slope. So I can say 20.615444. So with this value, uh, let's see whether our solution has approached or not. So our solution has slightly modified. However, still it is very far from the exact solution. So it means we have to update the slope. So we can work with a new value, and we can find that we can select that value intelligently by using the secant method. We have the equation for secant method as tk plus 1 from tk and tk minus 1. So I hope you know the derivation of this equation from secant method. So over here, let me correct this one. It should be tk plus 1, and it is the index of our calculation. So should be written as a subscript, but let's see, it is over here. So the new value that should be used as a as for the new calculation should be minus 16.586. So now we will solve this problem again for the new value of the slope. So I use it here, minus 16.586. So we get a new solution. So where that solution is, okay. So now the solution is below the computed value. So now we have the three slope values. So minus 16.586. So we have to proceed. So I will update the initial approximations. So here I have the numerical values. So I make it minus 1 value. I can select it, copy, and let me paste it. So, and the new slope value that we used, so this value has been preserved over here, so I can use it as minus 16.586, and the value of y I got with this slope was 12.73111. So the new value suggested by secant method is minus 13.4185. I provide it here, so minus 13.4187, and we compute the whole solution of second order initial value problem by using the RK4 method, and we can see that one over here whether it has converged or not. So we have approached even more closer to that. So I will then again update the initial approximations. So this will take the position of tk minus 1, and for tk I will use the current value, which is minus 13.4187, and the solution predicted over here would be 14.67153, adopted from column J32. So the new value has been suggested, minus 13.9707. So this will take a position over here, minus 13.9707. So let's see the solution. Oh, it's even better. So if you like, you can stop at this point if it has converged, or if you like, you can move further. For example, let me try one more iteration. The slope value I used was 13.97007, and the value predicted was 14.35067. Okay, so we got a new slope value, minus 14.0005. So very slowly and gradually approaching the solution. So let's do it on 5. Okay, So see, the final boundary has been achieved up to 3 decimal places, 14.333. So we have that. So that's how we work with the solution of boundary value problems. So if you like, you can go for a further calculation. Here, this value was 14.0005 and the value predicted 14.33315, and that's it. So next value is suggested as minus 14.0002, 14.0002. Okay, so now up to 5 decimal places. So that is the power of the numerical methods. So finally, we have approached the solution of 2-point boundary value problem, which was of non-linear type.